Yeah, we are now going to cover what we call variance of a continuous random variable. It can be capital X, capital W, so whichever variable is used, but we want to get the, the variance of such a variable. So we want to say that if capital X is a continuous random variable, with the PDF, small f of x, and then its variance, the variance of capital X, denoted by var of x is given by so the variance of a random variable capital X, var of x is given by the expectation of x squared minus the expectation of x all squared. So in some textbooks you may find the expectation of x when it is represented by mu. So the variance of x can be the expectation of x squared minus mu squared, where mu is the expectation of x. So we saw how to calculate the expectation of x squared. We also saw how to calculate the expectation of x. So just like the expectation, even variance has gotten some properties. So properties of variance of a continuous random variable capital X, because we are discussing the variance of a continuous random variable. So if A and B are constants, then the variance of capital X, the variance of A is given by the expectation of A squared minus the expectation of A, the whole thing squared. This is Roman 1. Okay, let's first have it as a property, then prove it. So the variance of the constant is 0. Draw. This is the variance of x. This x which is squared here is this one. This other x which is there is that one. So if we are proving the variance of our constant a is going to be the expectation of a squared. Here is this. That if you want the variance of x, you say expectation x squared. So our x is now a minus the expectation of a by the whole thing squared. So our expectation of a constant a is that constant. So the expectation of a squared, since a is a constant, even a squared will be a constant. So the expectation of a squared, which is a constant, is this constant. The expectation of a is the a, but the whole thing is now squared. So finally, you realize that the variance of a constant is 0. Roman 2. The variance of x is the same as a squared, the variance of x. So if we want to prove that, we equally say that the variance of x is the same as the expectation of x squared minus the expectation of but the whole thing squared, we are using this very property. So if you have ax, this one becomes ax but squared, then expectation ax, the whole thing is squared. So the variance of ax will now be, that is the same as the expectation of x squared minus, the expectation of ax, but the whole thing is squared. We are now interpreting our properties of expectation. So if you have s squared, the expectation x, that is expectation s squared, expectation x squared, minus the expectation of a, the expectation of x, the whole thing is squared. So our expectation of a squared is s squared, because a squared is a constant. Now expectation x squared minus our expectation of a is a, then expectation x, but the whole thing is squared. So our variance, this is now the proof. Our variance of ax will definitely become s squared, the expectation of x squared, minus s squared, then the expectation of x, but squared. So s squared is common, we pull it out, we shall have s squared into the expectation of x squared minus the expectation of x, but the whole thing squared, which is as good as having s squared, the expectation of x squared minus mu squared. This is now the value of ax, but we already saw that the expectation of x squared, we already saw that the expectation of 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 x squared minus mu squared is the same as the variance. So we shall have our variance of ax as a squared, the value of x. Now in Roman 3, we have the variance of ax plus b. When you distribute the variance, it becomes the value of ax plus the value of b. Oh, let me first give it as a whole, then you prove it. This is s squared, the variance of x. Proof. So our value of ax plus b is equal to, you can distribute the value, it's the value of ax plus the value of b. The value of ax is s squared, the value of x. The value of the constant, we saw that it is a 0. Then after the variance of ax plus b is s squared, the variance of x, Roman 4. The standard deviation of capital X is equal to the root the variance of x. So we now want to apply those properties in dealing with the continuous random variables, the PDFs. So we have an example that says that a continuous random variable x, has a PDF small f of x given by, so our small f of x is equal to, it is a third. This is when our x runs from 0 to 3 and it is 0 elsewhere. So required is to find Roman 1, the variance of x, Roman 2, the variance of 3x, Roman 4, the variance of 2x plus 5, this is Roman 3, then Roman 4, the standard deviation of capital X, and the Roman 5, so Roman 5 is now the standard deviation of 2x plus a 5 solution. The very first step is to identify your PDF that you have, and obviously the range, then the property of the variance will come in after defining the variance. So our f of x is a third. It is a simple PDF. It is a third. This is when x lies between 0 and 3, and it is 0 elsewhere. So our variance of capital X is supposed to be the expectation of x squared minus the expectation of x, the whole thing squared. So we are going to find each part separately. We are beginning with the expectation of x. So our expectation of x is going to be the integral from negative infinity to positive infinity of a third, of x, f of x dx. That is how we get the expectation. Now we replace the expectation of x will become the integral. Where there is negative infinity, we put a 0. Where there is positive infinity, we put a 3. Where there is x, you leave it. Where there is f of x, you replace dx. So we shall have the variance of the expectation of x as, so our expectation of x is now going to become, this third is a constant, so we pull it out. So it is a third, the integral from 0 to 3 of x dx. So our expectation of x will be a third. When you integrate x, you get x squared over 2, but we are integrating from 0 to 3. Putting the upper limit to be a third into 3 squared over 2 minus 0 squared over 2, which is a third into 9 over 2, which will definitely be 1.5. So this is the expectation x. But for us to get the variance, we also need the expectation of x squared. So we are also defining the expectation of x squared. Now our expectation of x squared is going to be the integral from negative infinity to positive infinity of x squared f of x dx. So our expectation of x squared for the PDF given is going to be, is running from 0 up to 3. So it is from 0 to 3. We have x squared, then the PDF is 1 over 3. Put here the PDF dx. So pull out the constant, we shall have a third, the integral from 0 to 3 of x squared dx. So we shall have our expectation of x squared as it is a third. When you integrate x squared, you get x cubed over 3, but you have integrated from 0 to 3. So putting the upper limit, the expectation of x squared becomes a third. Putting the upper limit is the 3 cubed over 3. Putting the lower limit, it is 0 cubed over 3. So we shall have a third into 27 over 3. And the expectation of x squared is going to be